Hello everyone and welcome back to our parallel processing class. In this unit we will talk about um, a broader introduction to the concepts of parallel programming and how these concepts relate to the GPU or graphics processing unit technology. Our primary goal here is to essentially look at the background that we all have in serial programming and um, basically to try to figure out and um, and uh, and look at means and ways that can translate into um, algorithmically parallel thinking. We don't at this point we don't consider any one of us, um, the students, to have any familiarity with parallel processing concepts. And from this point on, we'll have a kind of a shallow overview, or rather, if you want to think about it, a 50,000 feet view of the parallel processing concepts and their relation with graphic processing units, GPUs, and then in the later units we will delve into more specific um, concepts that pertain to GPUs. A significant number of our work in computer science has been essentially done so far. If you haven't done any kind of professional GPU programming or high performance computing programming, um, uh, a lot of the programs that we have developed, if not all of them, have been essentially serial programs. Programs that are um, designed to follow through one single path of execution. This is because the landscape of computing has been primarily dominated by serial programs rather than parallel programming. Parallel programming has been essentially quite exotic so far, and just a very few handful of groups in the country, if not in the world, have been essentially working in high performance computing technologies, essentially utilizing parallel processing. Most of the people that go to universities for computer science degrees, they uh, are generally interested in the mainstream applications of technology and computer science, as well as computer engineering. And these mainstream applications are essentially, as I said, dominated by serialized programs. And there's a good reason that a lot of students actually work with, or rather have their main interest in serial programming, is that because a lot of companies that are hiring, they are also requiring serialized programs, and so or rather used to. And parallel programming was very specialized and essentially applicable to high throughput academic research, as well as applications that you cannot essentially implement them and reliably deploy them in a serialized manner, because it would take forever to complete the serial program. And so scientists, programmers, and computer engineers in those kinds of applications will fall back to parallel programming. There are many languages and techniques out there that can be used for parallel processing. When you think about CPU parallel programming, and we'll talk about it a little bit later, we tend to look at massive computing cores in the form of central processing unit cores that communicate with each other, and they have a lot of computing power. Or we can talk about one single CPU and try to simulate parallel processing by time slicing and time sharing of the resource allocations that the CPU utilizes between the threads that we have. So these were the traditional paradigms of parallel processing. Then from that point on, we talked about cluster computing and nodes, and how you could try to simulate a hardware mechanism in which you would have a lot of computing units, and then you will be able to allocate resources between these units and perform your parallel computing in that sense. But then again, all these applications that I'm talking about so far has been a lot of it has been done or dominated by academic research and high performance computing applications, rather than just specific desktop applications and things that end up with the consumer market. Now, when you think about implementing your programs in parallel and writing algorithms in parallel, you need to realize that a lot of this has to be done and coupled tightly with the hardware. You cannot really have just a conceptual parallel algorithm that is just done and implemented in software, because after all, the end result of your algorithm would have to be a functional program, and it has to be deployed on a hardware that can be capable of supporting the parallel algorithm that you have in mind. Based off of this concept of hardware related issues coupled with the software implementation of your parallel algorithms, a couple of standards evolved. We talked about OpenMP as a standard parallelism within a single node that was designed to take care of shared memory between machines, and also work with multi-core processors. And also we talked about MPI, message passing interface standard, that addresses parallelism between nodes. Based off of these concepts, there are two primary architectures that are now available: the OpenMPI, or rather the message passing interfaces that are primarily targeting CPU-based parallelism, and then a recent advancement with which was developed by NVIDIA Corporation, the leading developer and designer of graphics processing units, and it is dubbed as CUDA. And so in this class we will be focusing a lot on the CUDA architecture and the CUDA parallel programming. Now, coming back to what we talked about, hardware links to parallel programming, as I said earlier, to be able to design a parallel concept, you would have to tightly link and couple that concept with the hardware architecture that you have at your disposal. This is completely in contrast to serial processing and serial programming thinking that we have in mind. When you're thinking about a serial algorithm, you don't necessarily think about the platform, the hardware that you're targeting, and you rely on your compiler to take care of your mapping and your resource sharing and all the things that go under the hood of your hardware architecture, and you solely focus on the algorithm itself. That's not the case with parallel programs. So as more and more cost-effective, faster performance units are being available, you basically will have a lot more at your disposal to be able to write your programs and make use of these additional hardware availability. The problem becomes the fact that most of the time when you have better CPUs with multiple cores, more memory, if you wanted to tap into that kind of additional resource, you would necessarily have to rethink and rewrite your code to be able to utilize the additional resources that newer computing units, newer hardware platforms will give you. To standardize these concepts on the CPU-based two leading APIs, two leading parallelism concepts and standards evolved. The OpenMP is a platform that's or a standard that tries to address the parallelism within a single node. That is, if you have one computing unit, potentially a CPU with a bunch of cores, and a lot of memory at your disposal, then what you will essentially, what OpenMP allows you to do is to be able to utilize your cores relatively easily in terms of programming, and to be able to parallelize your algorithms and get some acceleration out of the program. The message passing interface (MPI) standard, on the other hand, tries to address the parallelism between multiple nodes and is specifically designed for clusters of machines that are created and deployed within a well-defined network architecture. It's often used in supercomputing installations where you may have many thousands of individual nodes, and each node essentially is an independently working computing unit with its own central processing unit, primary and secondary memory storages, and all that sorts of hardware architecture with it. MPI is often used for these kinds of clusters. The problem with MPI is that since it relies on a network and all of the interconnections between the network, the network itself will become your bottleneck. Essentially, the dominating factor that determines the maximum speed of your cluster based computation and solution is going to be your internode communications. One of the interesting things about the MPI architecture and the node and cluster computation is the Amazon Elastic Cloud system from the Amazon Web Services application. If you go on AWS.com, you'll see that they have a lot of really nicely designed and deployed units out that you can create instances from their clusters, and to be able to do your cloud computing over the web. Both OpenMP and MPI can be used together to exploit the parallelism within nodes as well as across a network of a cluster of machines. However, the APIs and the approaches that are used for using OpenMP or MPI architectures are entirely different. That means that they usually don't work well together. The OpenMP allows the programmer to take high-level view of your parallelism, whereas the MPI explicitly tries to work on the communication models of making your programming work in that sense. With the revolution in the technologies of graphic processing design or the GPU design, and especially with NVIDIA spearheading the project, a revolutionary model, an architecture is developed, and NVIDIA is the sole developer and owner of this technology, meaning that the technology is only accessible and available if you're using NVIDIA hardware. And we have been working on getting this architecture set up for you in our labs in Sugar Land and Victoria, and hopefully by this time you have secured an NVIDIA based card, or make sure that you have access to the labs in Sugar Land or Victoria campuses to be able to write your programs. And this architecture is called CUDA. It's a GPU programming language that we'll exploit in this class, and it can be used in conjunction with both OpenMP and MPI, or just as a standalone directive that we will use and set of libraries with the C compiler, or rather our C++ compilers in Visual Studio. And it is a massively multi-core parallelism architecture. It performs both task and OS-based parallelism. as opposed to, but the majority of your model is built on massively parallelized cores of what we call streaming multiprocessing units, or SMs, and we will try to split the processing of a compute unit into a large number of independent processing units that then they can be outsourced themselves to smaller number of processing and simpler processing units, and then the end result of this massive processing done in parallel is going to be a much more efficient in terms of time and step complexity, and we'll talk about these complexities a little bit later, and a much more efficient program. When you look at a multi-core CPU, what we're looking at, and especially what OpenMP allows you to do, is what is called the OS-based parallelism. What you will do is essentially you split up your tasks, and then you outsource each of these tasks to a separate core, and hopefully these tasks are designed in such a way that there will be minimal interference between the cores and minimal competition for resource allocation. So, and as we are talking about, quad and dual core processing units have been out there for a while. Now we're looking at even 8, 16, and 32 even cores on a CPU. So this will become a very much norm in the very near future of our technology and computing architectures. But with CUDA, if you have experience with the CUDA architecture and CUDA programming and the models of programming using CUDA, you will have absolutely zero problem translating those into a CPU-based task parallelism architecture. The idea there is to create a thread of application of process, and which basically separates the execution flow within your program. And these threads may diverge and converge at some point in time to maintain the main execution flow of your program. What is interesting with CPU task parallelism, or OS-based parallelism, is that you usually have a very small number of cores. You usually have 2, 4, 8 to 16 cores, and even within one single core processing unit, your operating system can still perform task-based time sharing or time slicing to give you this very small version of parallelizing your algorithms. But when we talk about CUDA programming and GPU general purpose coding and parallel processing, we will potentially look at a very, very, very large number of threads. And at that point, it becomes obvious that no operating system or CPU can handle such massive parallelization to be able to perform the tasks that we are talking about. And we will actually accomplish this within GPU, because GPUs are essentially designed for such massive parallelization and massive multi-core parallelism. And CUDA gives you both the hardware architecture and mechanisms to do it, and the software libraries that you could do this large-scale parallelization with relative ease. Back to what we're talking about. You've got threads at the heart of your parallelism. So when we're talking about parallel programming, we don't really we stop at the concept of here is a program, it starts here and it ends there. That is gone at this point. We now are talking about a thread of execution. And the neat thing about this threads of execution is that if you have a parallelizable problem, which we'll see a little bit later, what kinds of problems are easily parallelizable and what kind of problems are not, you can have this massive number of independent execution threads to work on the problem at the same time, either on the same problem at the same time or on different chunks of the problem at the same time. So you basically create several copies of the same problem and run these problems in parallel. And at some point, you merge the results of your application. So it should be obvious at this point what starts becoming an issue. We've got problems of resource sharing, the problems of concurrency, and the problems of locality. And we'll talk about these things as we go on today. Alright, as we talked about briefly, with the introduction of threads and essentially a unit of execution of your program, you would start in parallel programming um, um, looking at several issues that you would not have to encounter with serial programming. And one of the most obvious ones is the sharing of resources. Typically, when you have a bunch of execution flows of your programs or a bunch of threads, and they're running in parallel, there is a lot of resources that needs to be shared. And so when you look at your hardware architecture, the most obvious area of conflict that may arise is the number of processors that these threads are being run on, and also the memory accesses to locations that the threads are sharing. And we'll look at these different areas of resource sharing and resource allocation a little bit later in the semester, and see what can be done about it, and how much of it is outsourced and put on the hardware to take care of by CUDA architecture, and how much of it is at the hands and under the control of the programmer. The typical idea of resource sharing is through the use of something like a lock or a token. And the way that this works is that when you have a bunch of threads that are competing to act for access to a specific resource, the first one that gets access to the resource before it's locked, it is going to own that resource and lock it up for the others not to be able to access the resource, and then it would do whatever it does to the resource. And when it's done, then it unlocks the resource. So the next thread in having access, that thread will be able to lock the resource and do the work, and so forth. And so here you can see a potential conflict. We are going to do parallel programming by splitting our processing into chunks of threads that they will be running in parallel. The problem then is that when they're competing for a resource, essentially they would have to go and stay in a queue, in a line, to be able to access and utilize that resource. So in the ideal case, in the absolute case of all these threads needing access to one singular resource, then basically, although you had split your program into parallel units of execution, they would have to run in serial. So now here you can see the potential conflict arising. Parallelization splits the execution of your program in multiple units that ideally you want them to run at the same time. But the problem is, if you have very few resources that all of them are competing to, or many of them are competing to having access, your program, although in a parallel model, it will end up becoming, in the execution of the program, it will become a serial program. We'll see this this conflict in writing our program to calculate a histogram, which is a perfect example of showing you resource sharing and this conflict, and show you how potentially a program that you may think is completely parallel and is going to run wonderfully, it fails miserably. And we'll see that a little bit later. Another a way of sharing the operation is by contention. Basically, you just let all your resources to access the shared location without you caring about the conflicts that arise as a result of this shared medium, shared resource being used and accessed by multiple entities. So if you have say one byte in the memory, and you have a bunch of threads that are competing to write into that byte, you basically can also, instead of locking the byte whenever a thread is writing or reading from it, and so thereby letting all these other threads wait at the door until this resource is unlocked so that they could access it, you could actually have everybody just read it right into this memory unit. The problem here is that, as you can see, threads may step on each other's toes. A thread may write 7 into this memory unit, while another thread may write 27. And so these conflicts, you will have no way of resolving this conflict. And so if the thread writing 7 is the first one and the one writing 27 is the second thread, then the out result of this write operation will be number 27. If the order is reversed, if the first thread having access to this unit is the one that's writing 27, then the one that has that's writing number 7 into this unit, it would be the second and the last one. So the number that would be stored in that memory unit is going to be 7. So is the number you're looking for, is it going to be 27 or 7? Or would you want the sum of these two numbers, or the average of these two numbers? These problems come at the expense of contention, and in a program you may not care about it. In a program all you may care about is the content of that memory unit being changed. And so if that would be the case, the result of both of these threads writing into the memory unit is going to be not a matter of importance for you, so you can actually tolerate the inaccuracies in your program, thereby speeding up the system. If you have if your program, if your algorithm needs the accuracy and reliable means of resource sharing between your threads, then you would and you cannot have all the resources to be locked up, because that would also take a hit on your performance of your parallel program. Then you'd have to rethink your parallel algorithm to be able to come up with a solution that is somewhere in between. This problem of shared resources in parallel programming is another area in which there is a lot of difficulty in terms of debugging. So if you're running a program and you think the program is hypothetically and theoretically sound and it's working, and you're getting the wrong results, you would essentially have to go back and try to exactly plow through the program and your hardware and see exactly what is going on that is causing the problems with the results that you're getting. And some of these problems may also be because of the fact that certain units of operations that we may think as one unit of operation, for example an increment. If we take a memory address in C++, for example, and say that, oh, I have an integer program, let's say an int I, and then my thread is basically doing I++. The problem is that, you know, this simple unit of operation I++ in C++, it is not one unit of operation, it's actually 3 units of operation. Your thread would have to read the content of I if I were a shared resource. So if this was a shared resource, then your program or your thread would have to read the current content of I, add 1 to it, and then write it back into the content of I. So if this current thread read the content of I and it was 27, and by the time it's incrementing it, it relieves the lock on the content. So another thread would read the value, and so they would essentially, in essence, read the same value, and both of them will increment the content of I. The problem will become that you wanted the result of both threads incrementing I, it would be twice adding to the I, but since these are 3 different distinct operations, you end up getting the wrong answer. We'll see this later on in the histogram program, and you'll see what happens here. CUDA gives you a nice looking architecture that helps with this resource sharing problem, this resource sharing paradigm. And the resolution comes with an interesting hardware plus a software component architecture, and that essentially allows for the threads to be able to communicate with each other or resource share with each other, as well as threads that will not have any sharing of resources. And this will basically gives you the flexibility as a programmer to port pieces of your programs and your threads that need shared resources, and keep the parts that don't need shared resources in a separate chunks of thread units. And this way you can get the speed and the parallelization that you need at a higher level, and also thread communication at the lower level. The way that it works in CUDA is that your threads will be wrapped into a bunch of different hierarchies, and the lower hierarchies, threads within lower hierarchies, they would have a capability of sharing resources, and we'll see this a little bit later with more detail, both in terms of software and hardware. And then threads at the higher level will not have the ability to share resources. Thereby, they will be able to run completely in parallel. So if you want to think about it as a higher overview of what CUDA provides you, is that in CUDA your model is a grid of blocks that would run in parallel, and your hardware will take care of allocating these blocks to streaming multiprocessors to ensure the maximum amount of parallelization that you get. And within these blocks, so between the blocks of threads, you have absolutely no sharing and no inter-process communication, which means that there aren't memory units as well as streaming multiprocessor resources that can be shared between these blocks. Thereby, you don't have any problem of resource sharing in that level of hierarchy. When you go inside of each of those blocks, then you would have warps of threads, and a warp is basically 16 or 32 threads that are going to be run on the same streaming multiprocessor, which means that these warps of threads, since they are run in the same streaming multiprocessor, they have the ability to share registers as well as memory units, or rather the L1 cache of that streaming multiprocessor. So you will have inter-process communication through the shared resources. And I'll show you how in program you can declare whether you have a global memory that your threads would read to and write from independently of each other, or you have a shared memory in which your threads will be able to communicate their data to each other. The first aspect of looking at concurrency in your programs, whether concurrency in your hardware architecture or the concurrency of the processes that you can make into threads that they would then run in parallel, is to think about a particular problem without regard to any implementation, and then consider that what aspects of that problem can be run in parallel. If possible, you should be trying to think of a formula that represents each output point, say it's of some function, of the input data, and look at how you can actually run each of these input point calculations, or each of these function calculations on your data points in parallel. For some problems, some algorithms, it may become a little bit difficult and kind of cumbersome to think about. For example, if you have to iterate over a large number of steps, for these steps, if you wanted to consider each steps or iterations individually, can you have the data points for the steps to be represented as a transformation of the input points, which then you can take and have an independent algorithm on its own, and so forth. And for some problems, they're essentially easy to do that. A significant number of problems, which are also known as embarrassingly parallel problems, it is rather easy to underline the mapping or the functionality that will run on an independent input point, and will give you a result completely independently. And we'll look at these embarrassingly parallel problems a little bit later on, when we run our programs. And one of the easiest communication patterns in that sense is going to be map communication pattern, gather communication patterns, and scatter communication patterns, and also the stencil communication pattern. That would be relatively easy and straightforward to implement them in in CUDA and in parallel in general. For example, matrix multiplication is an embarrassingly parallel problem. If you take two matrices and you wanted to calculate the output matrix, which is a multiplication of these two matrices, there is an underlying process that can calculate every single element of the output matrix by multiplying each row of the input matrix with the corresponding column of the output of the second input matrix and calculate them in parallel. So for example, if I have matrix A and B and I want to multiply these to give me matrix C, if say A has three matrices, three elements, A, B, C, D, E, F, two rows and three columns, and then I want to multiply this with H, I, J, K, L, M matrix. So this is my matrix A, this is my matrix B, and this is going to give me X, Y, Z, W as my output. It's easy to see how you can do this in parallel. See, for each matrix, you can actually run out 4 independent processes for each of the output elements X, Y, Z, and W. So for example, for calculating the X, all you need to do is basically to take the first row and multiply it column by column, element by element, with the first column of the second matrix. And that would give you the results, and then you add the results together, and that gives you the result. If you wanted to calculate that same thing for column Y, all you needed to do is to take the first row here and multiply it element by the second column. And this multiplication result will give you essentially the second element here. For element 2, 1, for element Z, you take the second row and multiply it element by the first row. And these two will give you that that element. And for the last element, you take the last row of the first column, first matrix, and multiply it element by element with the last row of your second matrix. And this multiplication, and then you sum the results up, and this gives you the values for your fourth element. As you see, this problem becomes embarrassingly parallel. You actually have a means of calculating each of the output elements independent of each other from the input elements. And it doesn't matter who's running when and how, as long as you can run the formulation, you can outsource them and make a thread for every single one of those and have them run completely in parallel. So this is easy to apply. Now, loop iterations are easy in that sense that you can formulate in parallel. Data point calculations and formulations, as you saw here, will be an easy mapping calculations. There are other applications that may be at first a little bit difficult to think about parallelizing. For example, sorting might be a little bit difficult to think of in terms of how you can parallelize it. Another application of parallelization that at first is a little bit difficult, but if you look at it, is going to make sense, and you can actually run efficient parallelization algorithms on, is the scan operative. For example, if you have a tally, let's say a checkbook that you're balancing, so you have a bunch of input data, X, and the output data is going to be the sum of whatever you have seen so far. So you have X sub 1, X sub 2, X sub 3, and so forth, and the output to be X sub 1, and then for the second unit to be X sub 1 plus X sub 2, and then for the third unit to be X sub 1 plus X sub 2 plus X sub 3, and so forth. This may look a little bit difficult at first in terms of thinking of it as parallel, but this actually is an interesting and very efficient parallel pattern, and we will talk about this parallelization a little bit later in the class. The problem actually is not generally is not the problem of how you write your program in parallel, how you reformulate, re-articulate your algorithm to make it parallelizable. It's more of the problem of resource sharing, as I mentioned earlier, is that how your data is shared. And for example, in the case of our matrix multiplication, it's not easy to see, because the result of calculating the output doesn't really matter, because all of the operations that are happening on my input data on matrix A and matrix B are basically read operations. So if while I'm calculating the value for X and calculating the value for Y, if both of these are reading from the input and output in a different order, it really doesn't matter. But if I had a problem that the thread as a part of calculating for X was also interfering with the values, say for A, B, and C, then it would actually matter between the two threads, because then they would be sharing information, and that potential sharing of information of the thread X and thread Y would have potential complications down the road. So you would have to be able to realize um, the resource sharing and have means and mechanisms to be able to do this properly, so that um, you would not interfere um, with the calculations of the threads. As I said, the CUDA model is a very nice model that is designed to take care of this kind of parallelization for us. The heart of the CUDA is the so-called streaming multiprocessors in terms of its hardware architecture. We'll get to this a little bit later in the next unit, actually, when we talk about CUDA hardware architecture. Basically, it splits your programs into grids of blocks that each will have multiple threads. So you have a grid. That grid will have a bunch of blocks in it. Each of those blocks will have a bunch of threads in them. And the blocks may run in any order. So one of the things that you cannot control as a programmer is which block would run first, or which block would run in what order. And in fact, we will have no control over which streaming multiprocessor is going to run the blocks. This may sound a little bit limiting at first, but it actually has a huge amount of benefit and advantages for us, that the hardware takes care of block assignments and streaming multiprocessor assignments. The problem or the idea here is that only a subset of the blocks will run at any given point, and and a block must execute from start to completion, and may be run on one of the streaming multiprocessors. And blocks can be allocated from a grid to any multiprocessor that has a free slot to run those blocks. So you may have multiple blocks hosting and being run on one single multiprocessor, and but the problem is that we will not be able to govern which multiprocessor takes over which one of the blocks. So this it brings the two ideas, which is basically one idea. The block threads within each block will not communicate with threads within another block. So there's no inter-block communication happening here. When you look at the relationship between grids and blocks, and then you go inside of each of blocks, then inside of each block you go into a deeper hierarchy, and what happens in there is that you have the same relationship, which is basically the relationship between threads within a block and between two different blocks. So within every single block, threads are wrapped in the so-called warps. And basically, when your streaming multiprocessor, a block is assigned to a streaming multiprocessor, the execution of the threads within that streaming multiprocessor is going to have certain level of dependence. And that is the level of dependence between the warps. So what is going to happen is essentially you've got a streaming multiprocessor, and then let's say that two blocks are going to be assigned to this streaming multiprocessor, and then these blocks will have a bunch of threads that are going to run. So these threads are going to be run in warps of 32 threads. So a warp is basically made of 32 threads, which basically means that when your streaming multiprocessor decides to run a thread, it basically compacts the threads in terms of their adjacency and wraps 32 of them in a warp and then hands them over to the hardware to process them. So when we talk about later on in terms of optimizing your processing, you will see that you can get huge benefits in terms of speed up if you basically coalesce your memory accesses and have your memory accesses to be done in a consistent contiguous chunks of 32 or 16 units at a time. This way, because of this hardware architecture underlying your thread executions, they would it would speed up your processes. A typical GPU can actually have on the order of 24,000 active threads. And for things like, for example, for Fermi GPU, you can define 65,535 times 65,535 times 1,536 threads in total. So that's a huge amount of threads that that you can run, and this is usually enough to cover almost any kind of processing that you want to use in one single node. And the catch is actually that with this massive amount of threads that you have, your processors, the things that your threads are capable of doing and should be doing, are going to be fairly simple processes. But then on the other hand, you have a lot of them, so you can actually outsource your processes and make your algorithm quite efficient. If you could actually make every single streaming processor busy at every single time, doing something, processing some thread that is solving towards the solution of the problem. Computing has, over the last decade or so, moved from limited computational truth booth of the processors to essentially moving the data, becoming the primary factor. And we will get, again, this is just an introduction, we will delve into this idea of locality later on, in that a lot of, especially when you're working with massively parallelizable programming, such as programming for GPUs and CUDA, a lot of the bottleneck, a lot of the problems that arise is not the speed at which you can process data, is rather the speed at which you can communicate the data, at which you can transfer data from one place to another. When designing a processor in terms of processor real estate, your compute units, your arithmetic logic units, are cheap actually nowadays. They can run an extremely high speed and consume very little power and physical space. But they're limited in terms of the use of their operands. The amount of data that can come through your memory connections from different levels of storage areas, be it your secondary storage, such as a hard drive, SSD drive, optical drives, USB drives, to your primary memory units, such as your RAM, to your various levels of cache, to your resident cache, to your processor register banks. In modern computer design, this is addressed by using the multiple levels of cache, as I mentioned, and we talked about it earlier. Cache works in the two different kinds of ways, and that is the proximity or locality, both in terms of spatial locality or address spaces in physical memory units, and in temporal location or temporal locality, or being close in time. Therefore, the data that you are accessing and you want to process more frequently is best to be processed in both of these kinds of localities. So for example, it's really ideal if you have a lot of data that is going to be frequently accessed to have them in closer proximity in terms of both the address locations where they are, and also in terms of when they are being accessed. If you try to optimize both these localities, you're going to speed up a lot of your processes, because the cache is designed to exploit these kinds of localities. In that, if you have data that is close by with each other and you try to access them with the same frequency or frequency of accessing close to each other, they're going to basically populate the cache in a manner in which that you can speed up the access, because different levels of cache are going to have different bandwidths, different speeds of access. And cache works in this principle, in that most frequently used data is going to occupy the faster levels of cache. So your hardware actually is taking care of doing that for you. And so if you, as the software designer, also make it easier in terms of both putting your data in terms of closer proximity in time, closer proximity in memory spaces, you're actually going to exploit further this hardware architecture and get better use of it. When you're looking at your GPU, especially in the CUDA model, there are still the concepts of cache, and we'll see that there are still different levels of cache. There are resident cache and off-chip caches in your CPU in your GPU design and architecture, but it gives you a little bit more control in terms of placing the locality of your programming or of your data under the programmer's controls. So, and this is what I'm essentially pointing to and wanting you to keep an eye on, in that for GPU programming, you have a lot more flexibility and a lot more ability and control over placing, and we will talk about it later, and I already briefly mentioned it, coalescing your memory accesses, which makes it easier and faster for your data to be communicated back and forth between your graphics DDR and your streaming multiprocessors, and even into the register banks of your simple processors there. And we will see this a little bit later. This is going to help a lot with increasing the throughput of your programs, compute times, compute units, and we'll talk about and define it formally a little bit later, and as well as decreasing the latency of your calculations. And both of these measures, latency and throughput, are measures that we are interested in optimizing. We want to maximize our throughput, basically maximize the number of operations that we do it in a second, while minimizing the latency or the delay between when we submit our task and when the task is done. And not all the time are these two measures cooperating. Most of the time they're running against each other. So we need to find out a trade-off between these two optimizations that would get the best out of our calculations. When it comes to parallelizing, now that we know a little bit about what we have at our disposal on the hardware level, it would be the time that we will be able to look at our programs and try to see what kind of parallelization can we get out of the algorithm. There are typically two different ways, two different kinds of mechanisms to look at. There are task-based parallelism and the data-based parallelism. I haven't talked about task-based parallelism, and probably we won't really talk about task-based parallelism, especially if our data patterns are not directly related to one single task. We will not see this parallelization much in this class, but they are typical of operating systems. And for example, in the operating system, the task-based parallelism that we have is in the form of multitasking. What we do have is, for example, we can run a bunch of different tasks, like such as your PowerPoint slide presentation and this video unit and the web browser and a bunch of different tasks that are running in parallel. And that's what the operating systems do. They basically parallelize a lot of tasks, and they do that at the instruction level and also at the data level. What we are mostly interested actually is in terms of database parallelism. Database parallelism refers to transforming the models of your data into a model that is parallel. instead of thinking your tasks running in parallel, what you want to do is that you want to run your task into separate chunks, separate pieces of your data, and run different pieces of data in parallel. So essentially, you have the same unit of tasks, but they are working on different areas of your data. And this is a good model for massively parallel processing units, and it's nicely done within our CUDA architecture, and we will see how it's actually taken care of a little bit later on. So as I said, with your task-based parallelism, you would work with a coarse-grained parallelization approach. You usually look at a bunch of different tasks, and you split those transformations into 4 separate and unrelated kinds of data, or 5 or 6 or 10. And then you would basically utilize each of your cores, your CPU cores, 4 CPU cores, 6, 10, 16, 32, however many CPU cores you do have, and outsource each of the tasks to each of your cores. So you could have a bunch of different kinds of processes that could be completely unrelated, and then you could timeshare them, basically have each core process each of the tasks for a certain period of time before moving to working on another task, and then going back and forth. You can also program in pipes. Basically, you will be able to share information between the pipes, and or also the so-called pipeline parallelism. And all of this is quite capable of running a small number of tasks that may also be shared between various cores of processors that you have. But the limit of this task-based parallelism is that you cannot really get a massive amount of parallelization out of this unit, because at some point in time your hardware resources are so rare. You have just so many processors, you just have so many cores, that you cannot split this into finer grades of parallelization. With your database parallelism, on the other hand, you can actually do this with a finer grade of parallelization. As I said, you can transform your data and fit it into parallel models, create simple little tasks that then you can assign chunks of data to these tasks and have them parallelize in massive numbers, and these will become the threads that we will be running. So basically, we'll create a bunch of very simple processes that will be working on different pieces of the data that we have, but we'll have them wrapped in a lot of cores, a lot of grids, and a lot of blocks, and a huge number of warps, and then we'll have them run. There's a couple of things that we need to be aware of, although it's very easy and straightforward to do, especially with CUDA. It's a lot of the messy parallel parts of it related to the hardware is taken care of, is that our processes needs to be fairly uniform in process. So we cannot have too many different kinds of processes, and because if we get to have different threads or different pieces of our execution to differ from each other too much, then we're going to end up with the so-called thread divergence. And the thread divergence is something that causes performance hits and performance drops in our parallelization. So so by making the processes too complicated, we're going to run against the goal of efficient parallelization by having our threads diverge a lot, so that there is going to be a lot of bottleneck in terms of memory communications, and it will slow us down a lot. Also, on the other hand, we don't want to have very simplistic processes on our threads, because then this would cause low residency, which means that then we would end up having a lot of our streaming multiprocessors just idle for just that one thread that is taking too long to finish. So so we need to kind of keep in mind these two ideas of divergence between our threads as well as our thread residency or our streaming multiprocessor residency. So on top of this, there's the memory units and different kinds of memory that we have at our disposal with CUDA and with our thread executions that we need to be aware of and we'll learn about in this class. And also we need to take care of our data sharing and thread communications and make sure that although we have a massive number of threads running in parallel, they're still running and competing for access to shared resources. And if they do, we need to make sure that this access to shared resources is done properly so that our programs would also run properly. We've talked a little bit earlier about single instruction, multiple data category of architecture earlier. And here I'll talk about this 4 categories of Flint's taxonomy that classifies different computer architectures as the number of instructions that your computer architecture is capable of operating at a time, as well as the number of data points that architecture can work on at a time. So this will give you 4 different categorizations. The simplest one is SISD, or single instruction, single data taxonomy. And that is generally, if you want to think about it, is a standard serial programming model on the software side that most people are familiar with. And this is essentially the model for a single core CPU that at an instruction set level, it is capable of running one operation on one data point at any given time. Now, if you wanted to create the illusion of parallelism with an SISD model, or single instruction, single data model, you could basically time slice. So you could have more complex processes and tasks, and then split them into simpler units of processing, and then switch back and forth your memory and your CPU resources. And this is essentially called time slicing or time sharing. On the other hand, there's the other alternative of having a computer architecture that is capable of running multiple instructions at the same time, and each one of those instructions is capable of operating on multiple data points at the same time. So this will become multi-instruction, multi-data architecture, or MIMD. MIMD systems are essentially, you can see them a lot in the dual or quad core machines, and they're going to become on the CPU level more and more mainstream. They have a pool of threads and processes and a bunch of CPU cores that then the operating system will allocate from these thread pool to n CPU cores, n being the number of cores that you have that can be independently run in terms of the hardware level. Each of these threads and processes will have an independent stream of instructions, and all of the complications of your logic control that operates and funnels through the data into the instruction is going to be contained at the hardware level. So as you can see, this becomes a very complicated architecture in the hardware design side of it. Somewhere in the middle is the SIMD, or single instruction multi-data architecture, and SIMD systems try to simplify the approach of MIMD, multiple instruction, multiple data systems, to, in particular, cover data parallelism models. And our CUDA architecture is a lot like this, especially in the thread block calculations and the thread block operations. It follows very closely SIMD models in that you follow a single instruction stream at any given point in time, but that instruction stream was capable of operating on multiple data units. And therefore, they require a single set of logic inside of the device to be able to decode and take care of the execution of your instruction stream, rather than having multiple instruction decode paths that then they would kind of intercommunicate and work together. By removing this process or complicated control logic, you'll free up a lot of your chip real estate, and then you can create smaller and cheaper operating units, which in CUDA term they're called simple processors within every single streaming multiprocessor, and then and so you would end up with much less power consumption, and therefore you can pack a lot of these kinds of processing units at much faster clock rates than you could with an MIMD. If you look at the benefits of going for a single instruction multi-data architecture as opposed to MIMD, is that a lot of the programming patterns that we eventually end up using these systems for are going to by nature follow single instruction multi-data patterns. For example, most of the time you're averaging a bunch of data in one way or another, not necessarily just adding them and dividing by total. You may have convolution calculations you might want to do, fast Fourier transforms, discrete cosine transforms, a lot of filtering calculations that engineering applications need to do, image processing applications. A lot of these applications end up at the very end being broken down into simpler chunks of instructions paths that would operate on a range of data, as opposed to, for example, what is twice the time of this particular data point, or what is the calculation of this function on this data point. You generally are working on what is the result of this function applied to a range of these data points. So this by nature fits in this SIMD model. So by we essentially going with the SIMD model, we are freeing up our CPU complexity. Therefore, we'll be able to create a lot more of these simpler processing units. But at the same time, being able to take care of a lot of the calculations that we wanted to perform at the first place, because they fit in this single instruction multi-data model of operation. So therefore, as opposed to just running one data unit operation at a time, we can actually run a bunch of data operations at the time as a part of one single execution call of our instruction set. And finally, we might have the complete opposite of the architecture, that we need multiple instruction units to run on a single data set or data point, and that fits with it brings us to the last architecture here, and it's the multi-instruction single data architecture, and or MISD. There aren't many examples and benefits of MISD out there, and so I'll just leave that as is. And if you're interested, you can just look into and explore a little bit more about this architecture on your own. But generally speaking, from this point on, especially when we're working on our GPU, the model follows SIMD very closely, and as such, it is imperative for us to know what this model entails and how we can exploit and use and benefit from formulating and creating our programs in such a way that they fit more closely into the SIMD model and architecture. And again, this brings me back to the same idea that I kept referring to without going into the details, and that is memory coalescing. And that is, it would be imperative, we would get a lot of benefits if we could write our programs in such a way that our data accesses are coalesced, and that when we have a single stream of operation, a single stream of instruction, for it to access not only multiple data units, but also multiple data units in such close proximity that we would not have to go back and forth all the way to the global memory, that we can actually host a lot of these data onto the chip, either in the register bank or at least in the cache, so that we would be able to faster access and to faster process this data whenever we need to access and process it. Any parallel program that you can think about, you can look at them at the in a certain way, and that is basically you can think of them as patterns. And in many different kinds of software and algorithms, you essentially the underlying processes are patterns of data communication. Although sometimes for some very simple or some complicated serial algorithms, it may be difficult to think of them as patterns. But if you think of your algorithm and the problem that you're solving in terms of patterns, you will be able to broadly deconstruct or make a form of abstraction of your problem that will help you more easily look at them and solve them. So before we get into the details of parallel programming and go through several very interesting and practical applications and parallel patterns that then we will use CUDA for implementing them, it's a good idea to go over and get a very basic overview of several important patterns that are intensively used in parallel processing. And we'll go through them. So we've got loop-based patterns, we've got fork-join patterns, we've got tiling and greeting, and we've got divide and conquer patterns. And I'll explain these a little bit, and then as we go on, we will go into and delve into more details of these patterns and even look at subcategories of applicable patterns of communication and processing. Loop-based pattern are probably the most familiar to almost anyone who's done any kind of programming. The primary concept here is that you have an iterative, repetitive process, and that you essentially will be able to terminate the repetition of the process by testing for a condition. And depending on whether you first test for the condition and perform your repetitive process, or perform the repetitive process and then test the condition, you will have pre-test versus post-test loops and repetitions. Also, you may have the case of a repetitive process that you know either the exact number of times that you want this repetitive process to repeat, or that you have a formulation of the exit strategy that depends on the number of times that your loop needs to operate. We call that a counter, and that gives you another case of, or actually a special case of loop. In programming, these loops are essentially in the form of for loops, while loops, and do while loops, and we are should be familiar with these three kinds of loops that if we have used any kind of C++ programming or C programming in the past. A loop-based iteration dependency is where one of your iterations of the loop depends on one or more of the previous iterations. If you're thinking about parallelizing this pattern, you would need to take care of dependencies or iteration dependencies, or be able to exactly formulate these dependencies so that your parallel implementation will not suffer as a result of neglecting these dependencies. Sometimes removing these dependencies are complicated, and those are the cases in which it would be a little bit difficult to take a loop-based pattern and make it parallelizable. And in some cases, this may just actually work counter to the idea of parallelization, and essentially make your parallel program run and behave as a serial program. So being aware and mindful of loop dependencies are an important step in parallelizing loop-based iterations. That being said, loop-based iteration is one of the easiest patterns of communication that can be done in parallel, or can be parallelized. If you have multiple loop dependent, if you have multiple loops, such as a nested loop with inner loop dependencies. If you try to take the dependencies from the inner loop out, then you'll be able to simply decide how to split this loop and then have an outer loop parallelized over your CUDA cores, or your CPU cores, and then have each of those cores take care of the inner loop processes, or do it the other way around. So this is one of the easiest patterns that you can parallelize in that sense. What you need to keep in mind when you're parallelizing a loop is that you should view your parallelization as minimizing the communication between processors, and maximizing the use of your on-chip resources, and that is your level 1, 2, and 3 cache resources on your CPU, or the amount of register usages versus, and as well as your shared memory usage on a GPU. And we'll get into the details of utilizing your shared memory in your GPU CUDA cores efficiently when we try to parallelize some of these loop based patterns. You should be looking at decomposing your macro level instructions based on the number of logical processing units that you have available. The good news is that with your GPU, you have a number of streaming multiprocessors, but each of these streaming multiprocessors can run upwards of 65,000 blocks, and each block can actually have up to about 1,024 or 2 to the power of 10 threads. So when you're looking at the number of iterations that you have in your loop, you would want to kind of look at, first off, what your hardware gives you in terms of resources that you have. Secondly, how resources as far as your hardware are designed, and how the communication patterns go between these different resources, and then try to map that into your logical view of your iterations, and then try to split your program up that way. This is in contrast to hyper-threading and core processing on your physical CPUs that you have. Notice that with a multi-core CPU, you have literally 4, 6, 8, 16, or however many, very few CPU cores that can truly take over your data in parallel, and the rest of it is going to be done through some hacks and tricks in terms of your operating system's time allocation. Whereas with your GPU, you literally have the streaming multiprocessors, each of which capable of running blocks of data independently of each other. And we'll tap into this notion, and we'll try to maximize our performance and our throughput of calculation, the number of operations that we calculate at a time, by utilizing our GPU streaming multiprocessors. The other patterns of communication that is common in serial programming is a fork join pattern, where there are synchronization points in your program, and what you can do, you basically have a execution path, and at some point of the execution path, you split the execution path into multiple execution paths, and from that point you have divergence in your code. Those multiple points of execution, paths of execution, will run independently of each other, and then at some point you basically join all those calls together through a join operation. This approach is typically found in OpenMP, where you define a parallel region with with a statement in your code, and then from that point your code splits into n threads, and later all those n threads will converge into a single thread again. So to, in terms of a fork join pattern of execution, you basically start with a path of execution, and then at the synchronization point you basically fork your paths of execution into multiple threads, up to n of them, and then at some point in time, or in path of execution, these guys are going to join back into one single thread. So as you can see, again, on a CPU with processing systems such as OpenMP, you basically can split truly in parallel paths of execution into the number of CPUs that you have available. So here, for example, you can split your execution into 4 paths and have them run in parallel, one path per processing element. And they can be truly independently run from each other, and write their calculations of your data into an appropriate destination in the queue. If you're using systems like OpenMP, you also have dynamic scheduling allocations, which basically mirrors the approach that are taken by GPU. In OpenCV, for example, the view of your processor of your threads is a pool of threads that are created, and only one task can be completed at a time. And therefore, if one task takes 10 times the amount of time that it takes for, say, 20 other tasks to complete, they're all allocated to only the free cores that are available. So as pools of threads are available, your scheduling mechanism basically takes threads out of the pool and gives them to a processing core, and only once the processing core is done with its execution, your scheduling mechanism will allocate and assign to that processing core another execution unit. So as you can see, this can, if you have threads that are highly divergent, if you have threads that do not run roughly in the same amount of operation and processing units, you essentially will slow down your process by not utilizing your processing resources to the fullest extent. If you have a thread that's taking way too long time than other threads in the pool, you're essentially, what you're making is that you're making a bunch of your processing cores, your units of processing, to basically idle while everybody is waiting for that one long thread to finish up. So when it comes to patterns of processing that are inherently categorized by a fork join pattern, you want to be mindful about what is going on in terms of the calculations that's going on within the threads that you have forked, and because there's synchronization issues, and you want to basically make sure that all of your processing units are busy doing something at all times. In terms of CUDA programming, we call this residency, and essentially, if you have a bunch of very fast threads and a very slow thread in a block of threads, this is actually a bad pattern, because usually what happens is that your blocks of code are a fork join pattern of execution. So when you're running a kernel, and we'll see how to write a kernel, how to invoke a kernel, and to execute them, when you're invoking a block of kernels, all other blocks of kernels would have to wait until all of the threads within that block are executed. So although you may have a bunch of very fast threads that might finish really quickly, the whole block would have to wait until everybody within that block is done. So that would cause occupancy and residency issues with your GPU cores. And later on we'll talk about these patterns in more detail. The approach that CUDA takes, which is sort of a different view, a different scheme than the fork join patterns, is the pattern of tiles and grids. CUDA uses this approach with all problems that you invoke, and it requires you as a programmer to break your problem into smaller parts. This is mostly interesting and very, very good in terms of utilizing your CUDA hardware, in that your hardware will take care of every little detail that needs to be going on under the hood in terms of your hardware architecture, and the allocation of threads per tasks or rather blocks per streaming multiprocessors. So you as the software developer won't be really bogged down with determining every single little thing that you need to do, but at the same time you have a lot of flexibility in terms of how you want to pattern, how you want to split your patterns and lay out the grids of blocks, and how you want to lay out the threads within the blocks. And as I explained a little bit earlier, is that you've got grids that are made of blocks. Each of these blocks are made of warps, and a warp is basically essentially 16 or 32 threads that will have coherent access to your memory and resonancy on your cache system and the register banks. So this is really nice, because a lot of parallel programs that you can utilize GPU acceleration on are inherently designed as grids. And for example, a lot of the programming modules that we do with this class deals with image processing. And image processing is an incredibly interesting application, in that each image is composed of a bunch of pixels, and each pixel will, depending on the kinds of image that you have, it may be a black and white pixel whose value may range between 0 and 255, basically an 8-bit value, or an RGB color value for each pixel. So if you look at an image, you by nature have a grid of data. And so CUDA will enable you to actually deploy your parallelized pattern that easily resembles the input data that you're working with. So this is incredibly interesting and incredibly important, that concept that you have at your disposal. And notice that although you may have a lot of CUDA cores that may be running, you're essentially limited with a smaller number of streaming multiprocessors. And they share your global memory, and within each of those streaming multiprocessors you have a bunch of simpler processors which will have some shared memory units, and each of those simpler processors will come with their own arithmetic logic units and register banks and smaller cache available to them. With this, a nice GPU, one single GPU, can operate at a peak speed of upwards of 3 teraflops. That's 3 terafloating operations per second, which is an incredible amount of processing power that just a consumer graphics processing unit, graphics cards, will be able to give you. This is impressive, and we will try to utilize this impressive amount of processing within this class, and look and design really nice programs that utilize CUDA in that sense. And finally, there is the ever famous divide and conquer pattern. That is also a pattern that inherently is designed by breaking up a problem into smaller subproblems, and then attempting to solve all those smaller subproblems separately, by in turn splitting those subproblems into smaller subproblems, and eventually once a smaller subproblem or sets of subproblems are solved, then we would merge back the results to solve the larger problem. And therefore we conquer the task of the computation that we have um, at our disposal. Typically, divide and conquer problems are in serialized processing uh, are looked at as a recursive calculation by nature, because what you will try to attempt is to take your large subproblem and split it into smaller subproblems of the same nature. That then you would call your overall function on this smaller subproblem by recursion, and this will solve your problem. A classic example of divide and conquer problem is quicksort. It recursively partitions your data into two sets with a pivot point. So you would have a set below the pivot point and a set above the pivot point. And you keep recursively partition your subsets, the set below the pivot and the set above the pivot, in such a way that they are sorted. And eventually, when you have sorted subproblems, you merge your results into bigger sorted arrays. If you look at these recursive algorithms directly, it may be incredibly difficult to break them up and make them into a parallel pattern and a parallelizable problem. But most of these recursive algorithms, you can also think of them as an iterative model, in which instead of recursing the same function over smaller subproblems, you're basically repeating the problem over and over, although on a different set of data at a time. And it is usually much easier to map onto a GPU pattern or a parallel processing or a parallel program or a parallel algorithm. And it fits better into a tile-based decomposition that we will talk about later on in our GPU resource programming and CUDA programming a little bit later down the semester. I think prior to Compute 2.0, recursion was not available, and in fact, I don't think I think Compute 3 point something introduced recursion, and we will not even touch on recursive parallel process patterns, because not only a lot of our GPU at least the GPUs that we have in the labs will not support it, but also it's a little bit difficult to really get to use efficiently recursive parallel patterns, primarily because there's a lot of overhead and inefficiencies in terms of data communication and communication patterns that goes on between the cores, and it makes it very, very difficult to detect and debug these problems. But we will talk a little bit about certain ways of looking at a recursive algorithm and then change it into an iterative process, which then we can actually implement. And in fact, I think toward the end of this semester, we'll talk about SCAN as one of the important parallel algorithms that has a lot of interesting usages, and then we'll try to use that pattern to reform some of the search algorithms that can be done recursively to do them in parallel. So with this, I'll close up this introductory lecture on understanding parallelism with graphic processing units, and next we will talk and look at our hardware overview that our graphics processing units, NVIDIA CUDA capable cards have, and how it, at least on a hardware view, how they look like. And then we will get into the programming portion and the software and algorithmic portions of the class. So with this, let you work on this unit and try to work on the student activities and participate in the discussion boards, and then I'll talk to you in the next unit about CUDA hardware architecture.